Hi everyone, welcome back to my Chemistry YouTube channel. In this video, we will discuss about hyperconjugation and its applications. Hyperconjugation involves in delocalization of sigma electrons of alpha carbon and hydrogen bond to the pi bond or p orbital to the pi bond or p orbital. In hyperconjugation, delocalization of sigma electrons of alpha carbon and hydrogen bond to the pi bond or p orbital takes place. We will see how it takes place by taking some examples. In hyperconjugation, we will consider case 1, that is in carbocations. In carbocations. Consider carbocation, that is CH3 CH2 plus. Here, the carbon which is bonded to carbocation is called as alpha carbon. And the hydrogens which are bonded to alpha carbon atom are called as alpha hydrogen atoms. Okay. Here, this hydrogen is bonded to alpha carbon. Here also, this hydrogen is bonded to alpha carbon. Here also, the hydrogen is bonded to alpha carbon. Therefore, this is sigma bond. This is sigma bond, which is made up of overlapping of p orbital of carbon and s orbital of hydrogen. I'll rewrite this molecule, that is hydrogen. Here also hydrogen. Here I am trying to show you the overlap of p orbital of carbon and s orbital of hydrogen. This is hydrogen, which has two electrons. And this carbon is bonded to carbocation. This carbocation indicates the presence of empty p orbitals. Okay, empty p orbitals. We know that electron move easily if p orbitals are in parallel position. This we have studied in the lecture inductive effect. The link is given in the description box. So here the electron move easily if the p orbitals are in parallel position. Here these two orbitals are parallel in position. So these electrons move to the empty p orbital of carbocation. Here this sigma electrons will move here. That means hydrogen, here also hydrogen. Here there is no bond between hydrogen and carbon, right? H plus, and here double bond CH2. Okay. If I rewrite this molecule, that is here hydrogen, carbon, here also we have hydrogen, and here the p orbital of carbon is overlapping with empty p orbital of carbocation to form carbon-carbon double bond. Okay. So these two p orbitals are parallel to each other, therefore they overlap to give pi bond. Okay. Here H plus. Okay. And here there is no bond between carbon and this particular H plus. Here this alpha carbon has 3 alpha hydrogens. So this sigma electron involved in delocalization. Again, here also this sigma electron involved in delocalization. Again, this sigma electron will also involve in delocalization. We will see how it is. Again, we will consider the same carbocation. CH, here CH2 plus, and here CH. 3 alpha hydrogens are there. This is alpha carbon atom. Here, this sigma electrons involve in delocalization. Therefore, that can be written as hydrogen here, C single bond hydrogen, here C double bond CH2, and here H plus. There is no bond between this hydrogen and carbon atom. Okay. Again, we have one more alpha hydrogen. That is, here sigma electrons are there. So, this sigma electron will also involve in conjugation. That can be written as here H plus carbon atom, here hydrogen and hydrogen double bond CH2. Here there is no bond between this particular hydrogen and carbon atom. Again, the carbocation consists of one more alpha hydrogen. This sigma electrons also involve in delocalization. So that can be written as H, here also H, and here H plus, no bond between carbon and this particular hydrogen, carbon double bond CH2. Okay. These are hyperconjugation structures. These are hyperconjugation structures. Hyperconjugation structures. How many alpha hydrogens are there? 3 alpha hydrogens are there. How many hyperconjugation structures are there? Again, 3 hyperconjugation structures are there. 3 hyperconjugation structures are there. So, in this case, delocalization of sigma electrons, delocalization of sigma electrons of carbon and hydrogen, here delocalization of sigma electrons of carbon and hydrogen bond to the p orbital of carbocation is taking place. Here sigma electrons are stabilizing carbocation. Sigma electrons are stabilizing carbocation. Okay. Consider case 2 in alkenes. Okay. Consider alkene. Hydrogen. Here also hydrogen. This carbon is attached to carbon-carbon double bond. Okay. CH2. So this is an alkene. Here the carbon which is bonded to carbon-carbon double bond is called as alpha carbon atom, and the hydrogens which are attached to alpha carbon atom are called alpha hydrogens. Okay. So here what happens is, again the sigma electrons are there. The sigma electrons of alpha carbon and hydrogen bond involve in delocalization. Therefore, this pi electron shift to here. Okay, if I rewrite this molecule, that is hydrogen, here carbon, hydrogen. Here I am indicating the overlapping of p orbital of carbon and s orbital of hydrogen, which has electrons. Okay, carbon, hydrogen, carbon single bond, CH2, and here the p orbital of these two carbon overlapped to give pi bond. Okay, this is pi bond. These electron moves easily to the p orbital which is parallel in position. That means here this sigma electrons are moving to here. If you write here H plus and here H and H, here double bond CH and single bond CH2 minus. Okay. Here there is no bond between carbon and this particular hydrogen because these sigma electrons are involved in bond formation. Okay, if I rewrite this again, what happens? Hydrogen, carbon, and here the p orbital of carbon, here we have hydrogen, CH, single bond, CH2, here also carbon has p orbital, here also p orbital. So these two p orbitals overlap to give pi bond. And here this carbon has a negative charge that is indicated in this way. Again, in this case, how many alpha hydrogens are there? 1, 2 and 3. 3 alpha hydrogens are there. So, all 3 sigma electrons are involved in conjugation. This will also involve in conjugation, and this sigma electrons are also involved in conjugation. We will see that. We will consider same molecule, that is CH, 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 and here CH double bond CH2. So this sigma electron involved in delocalization, therefore this pi electron shifted to here. That is CH, CH here H plus, and there is no bond between carbon and this hydrogen. Therefore carbon-carbon double bond CH single bond CH2 minus. Again we have one more alpha hydrogen. This sigma electron also involved in delocalization. So that can be written as here H plus, and there is no bond between this particular hydrogen and carbon atom. Here hydrogen, here also hydrogen, here carbon-carbon double bond CH single bond CH2 minus. Okay, we have one more alpha hydrogen. So this sigma electrons also involved in conjugation, that can be written as hydrogen, carbon, here hydrogen, and here H plus, there is no bond between this hydrogen and carbon atom, double bond CH single bond CH2 minus. How many alpha hydrogens are there? 3 alpha hydrogens are there. How many hyperconjugation structures are there? 3 hyperconjugation structures are there. Okay, here delocalization of sigma electrons of carbon and hydrogen bond, which is adjacent to the pi bond is taking place. Okay, here delocalization of sigma electrons of CH bond to the pi bond is taking place. Consider case 3 in free radicals. Consider a free radical CH3 C single bond CH2 free radical. Here this carbon atom is called alpha carbon atom, and the hydrogens which are attached to alpha carbon atom are called as alpha hydrogen. Okay, here this CH bond consists of sigma electrons. If this sigma electrons undergo homolytic fission, one of this electron combines with the free radical to form double bond. That is here H carbon, here hydrogen free radical, here hydrogen, double bond CH2. Here we have one more alpha hydrogen. Here also sigma electrons are there. Again, if this sigma bond undergoes homolytic fission, the one of this electron combines with the free radical to form carbon-carbon double bond. So that can be written as here hydrogen free radical, carbon, hydrogen, double bond CH2. Again we have alpha hydrogen, and this sigma bond undergoes homolytic fission. Therefore, one of this electron combines with the free radical to give carbon-carbon double bond. Here hydrogen, here hydrogen radical, carbon-carbon double bond CH2. So these are hyperconjugative structures, and it has 3 alpha hydrogens. Okay, 3 alpha hydrogens are there. Therefore, 3 hyperconjugative structures are present. Now we will define what is hyperconjugation is. Hyperconjugation is permanent effect. Hyperconjugation involves in delocalization of sigma electrons of hyperconjugation involves in delocalization of sigma electrons of carbon and hydrogen bond adjacent to the pi bond or p orbital is called as hyperconjugation. The delocalization of sigma electrons of carbon and hydrogen bond, which is adjacent to the pi bond and p orbital. This we have studied by taking examples. That is, in alkenes, in carbocations, and also in free radicals. Okay. This hyperconjugation is also known as no bond resonance. Hyperconjugation is also known as Baker-Nathan effect. Okay. This is about hyperconjugation. Let us go for orbital overlapping approach. First we will take carbocation, that is CH3 CH2 plus. I'll rewrite this: hydrogen, here single bond CH2. So here the sigma bond is made up of overlapping of p orbital of carbon and s orbital of hydrogen. Okay, and here this carbocation will be having empty p orbitals. Okay, this sigma electrons will move to the empty p orbital to form bond. Therefore, what it becomes? H, here hydrogen, here again carbon atom which has vacant or empty p orbital, here hydrogen and here hydrogen. So these two p orbitals overlap to give pi bond. In this case, overlapping between sigma electrons and p orbital is taking place. Sigma and p overlapping is taking place. Okay, this sigma electrons is of carbon and hydrogen, and this p orbital is vacant or it is empty p orbital. And here this carbon is of sp3 hybridized carbon atom, and hydrogen is of yes. Okay, so here the sigma and p orbital overlapping is taking place. In carbocation, sigma and p orbital overlapping is taking place. Let us take in free radicals. Consider a free radical. Here CH3, here also CH3 and CH2 free radical. This is the alpha carbon atom, and these are alpha hydrogens. I'll rewrite this: hydrogen, here carbon, here hydrogen, here the p orbital and overlapping of s orbital of hydrogen, and here CH2 p orbital of carbon which has one electron, right? This sigma bond undergoes homolytic fission, and one of this sigma electron combines with the free radical which is present in the half-filled p orbital. This is half-filled p orbital to form carbon-carbon double bond, that is H carbon, here hydrogen, and here carbon-carbon double bond, CH2 and here hydrogen radical. Here this sigma electron is overlapping with half-filled p orbital of carbon. The overlap is because of sigma and p orbital overlapping. Here this sigma electron is of carbon and hydrogen bond. Here carbon is sp3 hybridized carbon and hydrogen is of s orbital. Here this p orbital is half-filled p orbital. In free radicals, the overlapping is sigma and p orbital, which is half-filled, is taking place. Third one, in alkenes, we'll take an alkene, that is CH3, single bond, CH, double bond CH2. Okay, in this case, this carbon is alpha carbon atom, and these hydrogens are alpha hydrogens. These are alpha hydrogens. I am going to rewrite this again. Hydrogen, here carbon, here hydrogen. Here the p orbital of carbon overlapped with s orbital of hydrogen. Here CH double bond CH2. This pi bond is made up of overlapping between p orbitals of these two carbon atoms. Okay, which also consist of vacant pi star orbital, Okay, this is pi star orbital, that is nothing but anti-bonding orbital. Okay, so here the sigma electrons, here these two sigma electrons overlap with pi star anti-bonding orbital. In alkenes, sigma and pi star overlapping takes place. Sigma and pi star overlapping takes place. Okay, so again this sigma is of carbon and hydrogen, and here sp3 hybridized carbon, and here yes, this pi star is vacant anti-bonding orbital. Okay, in alkenes, the overlapping is because of sigma and pi star anti-bonding orbital. Consider CO and CN. Okay, so here this is C double bond O, and here C triple bond N. You can think that hyperconjugation is also possible in these two cases. Okay, because here also there is anti-bonding pi star orbital, and here also there is anti-bonding pi star orbitals. These two will not show hyperconjugation in these case. Okay, pi star orbitals will be having higher energy, anti-bonding orbital. So this anti-bonding pi star orbital will be having high energy in case of CO and CN. Therefore, in these two cases, hyperconjugation is not seen. Consider one more point. Here, hyperconjugative structures, which involving carbon and hydrogen bond breaking is equal to number of alpha hydrogen atoms. Number of hyperconjugative structures which involving CH bond breaking is equal to number of alpha hydrogen atoms. Again, if you consider hyperconjugative structures, simply hyperconjugative structure is equal to number of alpha hydrogen plus 1. In this case, it is not particularly mentioned that there is no carbon and hydrogen bond breaking. Okay, therefore, the hyperconjugative structure is equal to number of alpha hydrogen plus 1, and this one is of original structure. For example, if I take carbocation, this is the original structure. 3 hyperconjugative structures are possible because it has 3 alpha hydrogen atoms. If this sigma electron involved in delocalization, what will be the structure here? Hydrogen, carbon, here hydrogen, double bond CH2. Okay, here H plus. Here the bond breaking of carbon and hydrogen is taking place. Okay, and again, if this sigma electron involved in delocalization, what happens? Here H plus, carbon, hydrogen, here hydrogen, double bond CH2. Here carbon and hydrogen bond breaking takes place, and we have one more alpha hydrogen. This is also involves in delocalization, therefore that can be written as hydrogen, here H plus, C double bond CH2. These are hyperconjugative structures. How many hyperconjugative structures are there? 3 hyperconjugative structures. How many alpha hydrogens are there? 3 alpha hydrogens. So in this case, here breaking of CH bond is taking place. See, here also breaking of CH bond, here also breaking of CH bond, and here also breaking of CH bond. How many hyperconjugative structures which are involving in carbon and hydrogen bond breaking means number of alpha hydrogen atoms. That is 3 alpha hydrogen atoms, therefore 3 hyperconjugative structures which are involving in carbon and hydrogen bond breaking. To the same molecule, if the question is how many hyperconjugative structures are possible, that is equal to number of alpha hydrogen plus 1. How many alpha hydrogens are there in this case? 1, 2, 3. 3 alpha hydrogens plus 1. Okay, that is equal to 4 hyperconjugation structure. 3 plus 1, 4. 4 hyperconjugation or 4 hyperconjugative structures. That is, this is one hyperconjugative structure, second hyperconjugative structure, third hyperconjugative structure, and fourth hyperconjugative structures. To the same molecule, if the question is how many hyperconjugative structures involving in CH bond breaking, okay, for this question the answer will be 3 alpha H. Okay, for the same molecule, if the question is how many hyperconjugative structures are possible, for this question answer is 4 hyperconjugative structures. In question, if it is clearly mentioned the hyperconjugative structures which are involving in CH bond breaking, that is equal to number of alpha hydrogen atoms. In question, it is simply mentioned that how many hyperconjugative structures are possible, that is equal to number of alpha hydrogen plus 1. Okay. One more point, that is hyperconjugation. Hyperconjugation dominates over the inductive effect. That means hyperconjugation takes the preference over the inductive effect. Okay, so we'll take some examples. For this carbocation, this is the carbon which is alpha, and here also we have alpha carbon atom. Okay, how many hydrogens are there here? 3 hydrogens. 3 alpha hydrogens are there. Here also 3 alpha hydrogens are there. Therefore, how many alpha hydrogens are there here? 6 alpha hydrogens. 6 alpha hydrogens. Okay, next coming to a free radical. Okay, this is the free radical. This is the alpha carbon, and here this one is alpha carbon. How many alpha hydrogens are there? Here 3 alpha hydrogens. And here how many alpha hydrogens are there? Here only one alpha hydrogen. 4 alpha hydrogen atoms are there. Next we will take carbocation. Here how many alpha hydrogens are there? Here 3 and here 2. Therefore 5 alpha hydrogens are there. If we take an alkene, okay, this is an alkene. So the carbon which is bonded to alkene is called as alpha carbon atom. Okay, this is an alpha carbon atom. Here how many hydrogens are there? 2 hydrogen atoms. Therefore 2 alpha hydrogens are there. Consider, okay, so how many alpha hydrogens are there? This is alkene. The carbon which is attached to alkene is alpha carbon. Here alpha carbon is there. Here also alpha carbon is there. And here also alpha carbon is there. How many alpha hydrogens are there here? 3 alpha hydrogens. Here 2 alpha hydrogens. And here also 2 alpha hydrogens. 2 plus 3 plus 2 is equal to 7 alpha hydrogens are there. Okay. So in this way you have to identify the alpha hydrogen atoms. We will move on to applications of hyperconjugation. First one is to compare stability of carbocations, free radicals and alkenes. Okay, in hyperconjugation, stability is directly proportional to number of alpha hydrogen atoms. Based on this, stability is decided. Among these three, which is the more stable carbocation? That is the question. So here, this is the carbocation. This is alpha carbon atom, and here this is alpha carbon atom. This is alpha carbon atom. How many alpha hydrogens are there here? Here 3 alpha hydrogens, 3 alpha hydrogens, and 3 alpha hydrogens. Therefore, 9 alpha hydrogens are here. Coming to this case, here how many alpha carbon atoms are there? 1 alpha carbon atom and second alpha carbon atom. How many alpha hydrogens are there? Here 3 alpha hydrogens and here 3 alpha hydrogens. Therefore, 6 alpha hydrogens are there. Here, how many alpha carbon atoms are there? This is alpha carbon atom and here this is alpha carbon atom. Here 3 alpha hydrogens are there. Here 2 alpha hydrogens are there. Therefore, 5 alpha hydrogens are there. So, what is the stability order? Stability is directly proportional to number of alpha hydrogens. So, here 9 alpha hydrogens, 6 alpha hydrogens and 5 alpha hydrogens. Therefore, the stability order is first one is greater than, second one is greater than, third. This is the stability order. Consider free radical. Okay. Here this is the free radical. And again, free radical is here. And again, free radical is here. How many alpha hydrogens are there? Here 3 alpha hydrogens. This is also alpha carbon atom. This is also alpha carbon atom. Here 2 alpha hydrogens and here 2 alpha hydrogens. 2 plus 3 plus 2, that is 7 alpha hydrogens are here. And coming to this case, this is the alpha carbon atom and here this is alpha carbon atom. How many alpha hydrogens are there? Here 1 alpha hydrogen and here 2 alpha hydrogen. Therefore, 3 alpha hydrogens are there. Coming to here, this is the alpha carbon atom and here this is the alpha carbon atom. How many alpha hydrogens are there? Here 2 alpha hydrogens and here 2 alpha hydrogens. Therefore, 4 alpha hydrogens are there. What is the stability order? If you consider this is A and B and this is C, what is the stability order? A is more stable than, C is more stable than B. This is the stability order. This is alkene. One more example. Okay. Among these three, which is the most stable alkene? Based on hyperconjugation, you can easily solve the question. That is, this is alkene. How many alpha carbon atoms are there? Alpha carbon atom, alpha and alpha carbon atom and alpha carbon atom. How many alpha hydrogens are there? Here 3 alpha hydrogens 3 alpha hydrogens and 3 alpha hydrogens, 3 alpha hydrogens. How many alpha hydrogens are there? 12 alpha hydrogens are there. Okay. And coming to here, this is alkene. Okay. Here alpha carbon and alpha carbon. How many alpha hydrogens are there? Here 3 alpha hydrogens, 3 alpha hydrogens and 3 alpha hydrogens. How many alpha hydrogens are there? 9 alpha hydrogens are there. Coming to here, this is alkene, alpha carbon atom and alpha carbon atom. How many alpha hydrogens are there? 3 alpha hydrogens and here 3 alpha hydrogens. Therefore, 6 alpha hydrogens are there. What is the stability order? 12 alpha hydrogens, 9 alpha hydrogens and 6 alpha hydrogens. Therefore, stability order is first one is more stable than second one is more stable than third. This is the stability order. If you consider here, how many alpha hydrogens are there? This is alpha carbon atom and here this is alpha carbon atom. How many alpha hydrogens are there? 3 alpha hydrogens and here 3 alpha hydrogens. Therefore, 6 alpha hydrogens are there. This is alpha carbon and here this is alpha carbon. How many alpha hydrogens are there? Here 3 alpha hydrogens and here 3 alpha hydrogens. Therefore, 6 alpha hydrogens are there. Based on hyperconjugation, the stability of these two compounds cannot be decided. Therefore, you have to go for inductive effect. As I said earlier, hyperconjugation takes the preference over the inductive effect. Okay. So, here you cannot decide the stability order based on hyperconjugation. Therefore, you have to go for inductive effect. This is negative inductive effect and here also this gives negative inductive effect. If you write the order of power of negative inductive effect, NO2 is more electron withdrawing group compared to CN. Okay. Therefore, this negative inductive effect decreases the stability of carbocation. We know that stability of carbocation is directly proportional to plus M effect and plus I effect and inversely proportional to minus I and minus M. Okay, here this minus I effect decreases the stability of carbocation. This is we have studied in the inductive effect and also in resonance effect. Both are negative inductive groups. So among these two negative inductive group, which is the more negative inductive group means NO2 is more negative inductive group. Therefore, it decreases the stability of the carbocation when compared to CN. Therefore, the stability of 2 is greater than 1. This is the stability order. We'll take one more question. So here, how many alpha hydrogens are there? Here 3 alpha hydrogens and here 2 alpha hydrogens. Therefore, 5 alpha hydrogens are there. Here how many alpha hydrogens? 3 alpha hydrogens and here 2 alpha hydrogens. So, therefore, 5 alpha hydrogens are there. Based on hyperconjugation, the stability of these two compounds cannot be decided. So, therefore, we have to go for inductive effect. We know that this is negative inductive group and here this is also negative inductive group. Which is the more negative inductive group? NO2. NO2 is the more negative inductive group. Therefore, this is A and this is B. Here, this NO2 group is more negative inductive group compared to F. Therefore, the stability order is B is more stable than A. This is the stability order. We will take one more question. That is, if we take, okay. So, what is the stability order? This is A and here B and this is C. This is alkene. How many alpha hydrogens are there? Here 3 alpha hydrogens and here 3 alpha hydrogens. Therefore, 6 alpha hydrogens are there. Again, this is alkene. How many alpha hydrogens are there? Here 3 and here 3 alpha hydrogens. 6 alpha hydrogens. And here alkene. How many alpha hydrogens are there? Here 3 and here 3 alpha. Therefore, 6 alpha hydrogens are there. Here also, based on hyperconjugation, you cannot decide the stability of these compounds. Now, you have to go for inductive effect. Here, this CH3 group is positive inductive group and here also CH3 group is positive inductive group. Here we have again CH3 group, that is positive inductive group, and here also positive inductive group. Here also positive inductive group, and here positive inductive group. In the first case, two positive inductive groups are attached to same carbon atom so that the positive inductive effect is more. Okay, therefore A is more stable. In B and C, two positive inductive groups are present at two different carbon atoms. In C, since both positive inductive groups are facing towards the same side, here the repulsion arises. But in B, since two positive groups are facing in opposite direction, therefore there is no repulsion, therefore B is more stable than C. This is the stability order. And second application is bond length. So here bond length is directly proportional to number of alpha hydrogen atoms. Here bond length is affected due to hyperconjugation. Bond length is affected due to hyperconjugation. For example, consider alkene. This is an alkene. Okay, CH3, CH double bond CH2. This is an alkene. This is alpha hydrogen and this is sigma bond which contains sigma electrons. What happens? These electron comes here and this pi electron shifted to here. So what is actually happening is, if you consider, this is the first carbon atom, second carbon atom and third carbon atom. It gives H single bond C, H single bond C, here double bond CH single bond CH2 minus, and here H plus. Okay. So here the single bond between first carbon and second carbon is converting into double bond, and the double bond between second carbon and third carbon is converting into single bond. Therefore, the bond length is affected due to hyperconjugation. Here, bond length of carbon and hydrogen bond is more than expected. And here, the bond length between C1 and C2. Okay, the bond length between C1 and C2. Here the single bond is converting into double bond. Therefore, C1 and C2, the bond length between C1 and C2 is less than expected. And coming to next, the bond length between C2 and C3, that is here double bond is converting into single bond. Therefore, C2 and C3, the bond length of C2 and C3 is more than expected. And we know the bond length order. That is, alkyne is less than alkene is less than alkane. This is the bond length order. So here the bond length between C1 and C2. Okay, this is the single bond and it is converting into double bond. Therefore, bond length is decreased. And coming to here, the C2 and C3, your double bond is converting into single bond. Therefore, bond length is more than expected. We will take one example, that is, consider CH3 single bond, CH double bond, here CH, CH3. Okay. And this is A, consider this is A and B, that is CH3 double bond, here CH3 and here CH single bond CH3. So among these two, which is the more stable? Among these two, what is the bond length order? Among these two, which has more bond length? Here this is alkene and here we have alkene. This is alpha carbon atom and alpha carbon atom. Here alpha carbon atom. How many alpha hydrogens are there? Here 3 and 3. 6 alpha hydrogens are there. Here how many alpha hydrogens are there? 3 plus 3 plus 3. Therefore 9 alpha hydrogens are there. Here 9 alpha hydrogens and here 6 alpha hydrogens. Therefore bond length of B is more than A. This is the bond length order. Here we are discussing the bond length of carbon-carbon double bond. That is nothing but bond length of alkene. Here you can note down one more point, that is in alkenes bond breaks during hyperconjugation. Therefore bond length increases. In alkenes bond breaks during hyperconjugation. Therefore bond length increases. This is about applications of hyperconjugation. Coming to types of hyperconjugation, the first one is isovalent hyperconjugation. Here all hyperconjugative structures have same number of bonds. Carbocation and also in free radicals. We will take an example. Here CH3 and CH2 plus. Okay, this is carbocation. So here 3 alpha hydrogens are there. If this sigma electron involved in delocalization, what happens? That can be written as H, C, here H and here double bond CH2. So here how many bonds are there? 1, 2, 3, 4, 5, 6. Okay, 6 bonds are there. Coming to here, how many bonds are there? 1, 2, 3, 4, 5 and 6. 6 bonds. Okay. In isovalent hyperconjugation, all hyperconjugative structures have same number of bonds. Okay. For example, carbocation and free radical. Second type is sacrificial hyperconjugation. In sacrificial hyperconjugation, one of the hyperconjugative structures have less number of bonds. Okay. For example, in alkenes, consider alkene. This is CH3, single bond CH, double bond CH2. Here 3 alpha hydrogens are there. This is the sigma bond which consists of sigma electrons. Here this sigma electrons involved in conjugation. This pi electron shifted to here. So you can write it as H, C, H, here H plus, double bond CH single bond CH2 minus. Here how many bonds? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 bonds are there. Okay, coming to here, how many bonds are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 bonds are there. In sacrificial hyperconjugation, one of the hyperconjugative structures have less number of bonds. For example, alkenes. Okay. So here this hyperconjugation is also called as no bond resonance, because here you can see that there is no bond between this carbon and hydrogen. Therefore, hyperconjugation is also called as no bond resonance. Third one is Reverse hyperconjugation. Reverse hyperconjugation. So what happens in this case is, here delocalization of pi electrons to the vacant orbital takes place. So in reverse hyperconjugation, delocalization of pi electrons to vacant orbital takes place in the presence of electronegative atom which attract the shared pair of electron towards itself. For example, consider carbon which is attached to three halogens. Consider carbon which is attached to three halogens, single bond CH, double bond CH2. We know that halogens are more electronegative. Therefore, it takes shared pair of electron towards itself. So what happens then? This pi electron shifted to here. Okay, that is here X, single bond C, single bond X, here double bond CH, single bond CH2, and here plus. Okay, and here we will be having X minus. We have one more halogen. If this halogen takes the shared pair of electron towards itself, okay, what happens? X minus, here X, and here C double bond CH, single bond CH2 plus. Okay, if this halogen takes the shared pair of electron towards itself, what happens? That can be written as X, here carbon, here X, and here X minus double bond CH, single bond CH2. Okay, this is nothing but reverse hyperconjugation. Due to reverse hyperconjugation, positive charge created on carbon chain. Positive charge created on carbon chain. But due to hyperconjugation, negative charge created on carbon chain. This is all about hyperconjugation. If you found this video helpful, do like, share and subscribe. Thank you for watching.